Hello, everyone. It looks like the room's still filling up, so let's wait another minute or two, and then we'll go ahead and get started. All right, it is a couple after. We'll go ahead and get started. All right, so hello and welcome to this discussion on ETL versus ELT architectures for continuous data streams. I will be your host and moderator. My name is Bjorn Carlson. And first of all, we want to thank you for spending your time with us, and we hope you find the content today valuable. A few housekeeping items before I introduce the main speaker. First, we will record this webinar, and we'll make both the recording and the slides available to you after this session. During the webinar, please use the Q&A button at the bottom of your screen to submit questions. We will do our best to answer all the questions during the session. If we cannot, we will follow up with you after the webinar. Our main speaker today is Jason Hall. He is a senior solution architect with Upsolver. And with that, I'm going to turn it over to Jason.
Awesome. So yeah, thanks, Bjorn. Really excited to speak with you all today. This is a topic that is obviously top of mind for all of you, given that you're willing to spend an hour with us on today's session. And I always like to start these types of presentations by learning a little bit about who I'm speaking with. So I'm going to launch a poll through Zoom, and I'd love it if I could get some feedback from everyone. Some general questions, where you're calling in from, some of the platforms and technologies that you're using, and really trying to gauge where a lot of you sit in terms of your current data architectures. And so if you're in the Zoom meeting, go ahead and check out that poll, and I'd love to, again, just kind of learn about the audience. While that happens, I will just echo Bjorn's comments. We obviously have all the phone lines muted for audio quality reasons, but I definitely do want to encourage any and all feedback, as well as questions that you might have as we go through the session. I will try my best to keep an eye on the Q&A panel as I'm presenting, but we also do have planned to keep 5-10 minutes at the end of the session open so that we can go through as many questions as you all might have. So getting a lot of responses here. This is cool. I'll actually share the results with you once we finish. Looks like we've got a lot of traditional ETL users out there, which is to be expected. Most of our audience, we've got 3 different continents represented so far. So no one from Antarctica, but I guess that's not surprising. And you know what? That's good. Let's go ahead and get started. We also have a kind of brand new audience to Upsolver. So that'll be good. Hopefully you'll not only walk away with this with some best practices around designing your data integration strategies, but also get a real solid understanding on who Upsolver is and what we do. Right. So I'll share the results there. Everybody should be able to see them, and we'll go ahead and get started with today's content. So I thought I'd present this session by going through a bit of I don't want to call it a history lesson, but maybe a story on how we got to where we are today. And so if you go way back to where, many of us might have started our data careers or data journeys, a lot of organizations started with, some sort of database where they stored their, operational transactional data in. Maybe there's a finance database that your business maintains to keep financial transactional records, right? And, one of the reasons you use those databases is so that we can run queries against it to produce reports, right? I'll simplify a use case around, we've got financial data stored in a transactional database. We now need to run reports against it so that our business users can analyze the performance of our business, right? Maybe look at sales by month or sales finances by, some aggregated time range. So that works to a point. Our business starts small, our database is relatively small. We connect Excel to it. We can create a chart or a graph pretty easily. But eventually your data volumes grow, right? So the amount of data that we need to report against, whether finance data or some other purpose, gets to be big enough that we can't reasonably run those reports against the source database itself. All right. Because when we run those reports, it slows down all of our transactional processing, right? We could have outages or we could have performance issues affecting our end users because we're running these reports against the source data, right? And by no means do we want to start having website transactions time out or users not able to give our business money because some business analyst is trying to run a report that happens to access our source data. So one way we address that is by standing up these separate databases to run reports against, right? So instead of these reports running directly against the source databases, they ran against some copy of that source data in a reporting type database that we could run reports against, right? And this solved one of those problems, right? We no longer had our reporting users interfering with our application users. But we needed to figure out a way to load that reporting database with information that we could report against. So we typically did some kind of batch load, right? Maybe a nightly batch, maybe a weekly batch where we'd schedule some sort of job to run that extracted some data from our finance database, put it into this reporting database, and then we ran our reports directly against it. And that worked to a point. But then we got to a point where our reporting became too slow, right? So we solved the problem of reports interfering with application users, but we eventually had a new problem pop up. And I've been in IT for a long time, so I always hate these subjective terms like slow, right? What does slow mean? Well, it could mean a few different things, right? It could mean that we're sitting in some reporting interface like Excel or Power BI, whatever it is, right? And it's just, we're sitting at an hourglass waiting for it to get us data, right? And business analysts don't like that, especially if these are executives, time is valuable. If they have to spend 5 minutes waiting for a report to generate, that's not very productive use of time. So that could be an indication of slowness, right? Just that the sheer ability for that report to deliver the data that it needs takes too long. But another slow concept could be that the report isn't as up to date as we'd like it to be, right? For example, we don't want to have to wait till the end of the month to see how our month is trending, right? So we need weekly metrics. We need daily metrics. Eventually, we might want metrics more frequently than that. So this whole slow idea is simply that the reports that we're running against these databases aren't as fast as they should be in terms of how fast they take to run and how fresh the data is. So we started to solve this problem by introducing data warehouses, right? Instead of just having this copy of our application database in a separate database that we can report against, we have this purpose-built system, i.e. a data warehouse, that can service up reports very quickly, right? And the data structures and the data accesses are designed in such to be analytical, right? So we can crunch and process large volumes of data and produce reports very quickly, both in the speed that the reports take to run and the freshness of data that those reports can deliver. But with data warehouses, this whole batch loading process wasn't effective, right? We couldn't just take a copy of our application database and drop it into a data warehouse and then make that be fast, right? We had to now integrate the data from our application database into the data warehouse and into a model that data warehouse enabled very fast and efficient analytical queries, right? And so I termed this kind of data integration, right? How do we integrate our data from our source database into our data warehouse so that it can efficiently serve up analytical queries and reports? And so as we kind of thought through data integration, we kind of have to fall back on a few questions, right? So what are the things that we need to consider when we build out these integration practices? And again, this is all about getting data to our users. We need to first determine how do we format that data based on the business logic that is driving our reports, right? So kind of like the schema of that data. You know, this might not be the same as the schema on our source system. It might be different. We might need to model it, build a star schema, build some sort of representation of that data in a way that the business needs it to be able to slice and dice and process the types of analytics that they want to do. We also need to consider the freshness that they require that data. Remember, one thing about a report being slow could simply be that it's too slow getting data into that report for us to analyze, right? In other words, we want to analyze our current performance, not performance from a month ago, but that just is, you know, all we have is data from a month ago. So we have to build our data integration processes to deliver data freshness that matches what the business needs in terms of the types of analytics they're trying to perform. And then finally, at a cost that justifies the use of that data. All right. Now, I think all of us have probably been a part of data infrastructures where maybe cost was one of the final things that we considered. And maybe we got shocked by the cost that it took to build out a data integration process. But this has to be part of the equation, right? We're not going to spend millions of dollars building a data integration architecture if the value of those reports doesn't match that $1 million that we're investing, right? It's just a pure ROI conversation. So all these things kind of go into how we need to define and build out, you know, our data integration strategies. And to address these considerations, ETL was kind of born. Right. So if you think back, you know, 10, 15, 20 years ago, kind of as this data infrastructure really started to take shape, the way that we address data integration is through an ETL workflow that to feed into our data warehouse, right? We have our raw data over on the left-hand side of the screen. So that's could be our finance database or our CRM or our, you know, whatever the data might end up being. It's stored in some database, right? Oracle, SQL Server, DB2, MySQL, any number of the database platforms. So ETL effectively defines we need to extract data from that source. We need to then transform that data into the model that defines our business logic. And then we need to load that refined data set into our data warehouse for reporting, right? So really the ETL approach, the ordering of those letters is of course important because it defines the flow of data as we integrate it into our data warehouse. We extract it, then we transform it, and then we load it. An aside about transformation, we're going to be talking about transformations in a few different ways during today's session. Transformation is kind of like a catch-all for all the different things that we might need to do in order to produce those analytics-ready data sets, right? So we might need to cleanse data. Maybe we've got some bad data in the source, so we need to either redact that out or normalize it or fix it. We might need to enrich data. We've got data coming from multiple sources. So maybe we need to look up like a employee ID and find out where that employee lives, right? In our refined data set. We might need to aggregate the data, which is a very common reporting use case, right? I've got transactions at the second level in my raw data. I want to aggregate that into an hourly aggregate and write that into my data warehouse. So all these things all these transformation processes are happening in between our source data and our data warehouse. And in that transformation layer, we have dedicated resources handling that processing, right? There were entire platforms built out that served the sole purpose of transforming data, all right? Many of these are still in use today and remain very useful for the purpose that they were built. Platforms like Informatica, SQL Server Information Services, integration services. But these are dedicated platforms with dedicated storage and dedicated compute that serve the purpose of transforming source data prior to loading it into a target system, right? And in many ways, these platforms are proprietary as well, right? They kind of have their own programming languages, they have their own methodologies, their own workflows. But again, they were purpose-built to efficiently handle transforming source data and putting it into a format that could then be analyzed and stored in a data warehouse. And with these, I'll use the kind of air quotes here, traditional ETL systems. Again, we had to consider that we had dedicated and separate infrastructures required for that transformation, right? Compute and storage that served the sole purpose of transforming source data. Now, the second bullet here, that's both a benefit and a consideration, I should say, but only that transformed data is sent to the warehouse. So in other words, we're running reports against data that has already been transformed. And the only data that we have in our data warehouse is that which has gone through our transformation layer, right? This transformation layer to those analytics users is often kind of a black box, right? Now you could think through and you may say, well, that's a good thing, right? I don't need my business users, my analyst users. They don't need to see inside the machine to see how those transformations were applied, right? I just want to send them refined data sets and allow them to run reports against it. But that's a consideration, right? And that all that ends up in the data warehouse is data that's already been transformed. And kind of a caveat to that consideration is that data retention has to be managed in the source system, right? So if you go all the way back to the left-hand side of the diagram, that raw data, right, that's where data is retained. These transformation layers work on subsets of data. We bring a subset of data in, run the transformation on it, and then write that transformed data out. But we're not working on the entire data set all at once, right? And so if we need to maintain 7 years worth of historical data for a variety of reasons, that data retention is typically maintained at the source system, right? And there are implications there that we'll discuss as we go through this session. Sorry, I jumped the gun here. So data retention, why might we need to retain data, right? So there's lots of reasons. None of these are likely a surprise to most of you on the call. But first and foremost, there are compliance regulations that require us to maintain data, right? So there's lots of them out there that say you need to keep N years worth of data. Should there be should we have to legally look into, your data, right? Or should we need to go back in time and see what was happening and when? But there's also kind of non-compliance related things to consider when coming up with a retention strategy. For example, fairly often the business has new ways that they want to analyze existing data, right? Let's say we've been keeping transactional data for 5 years. And for those 5 years, we've been doing historical analysis on financial performance. But now we want to start maybe doing some machine learning or predictive analytics on that data, right? The same data that we've been generating for the last 5 years, just a new way that we want to analyze it. And it'd be a bummer if we decided we only wanted to keep 1 year's worth of data because that's all we thought we would need it for our financial reporting, only to then have that prohibit us from having 5 years worth of historical data to build predictive models on our performance, right? So that's honestly something that I see a lot of customers now starting to struggle with. They have these new ways to use data, but they didn't retain their source data long enough for them to effectively use that data in the way that they want to use it for. The third bullet that becomes important there is this concept of bad data, right? Fairly often, everybody's probably gone through this in the past, but we're generating data at the source. So we assume that it's good data. We feed it through our ETL pipelines. We produce reports against it. And only after the fact that we realize something's not right, right? Either some data was inputted improperly, or transformation logic was broken, but regardless of the reason, we ended up with bad reporting. And we don't want to throw that report out, right? We'd like to still be able to leverage that report for analytics, but we're going to have to go back and correct what caused the problem in the first place. That could be correcting the source data or correcting the transformation logic that applied to that source data to provide our analysis. But both of those processes need a data retention policy that's going to allow for you to go back in time and correct and fix the bad data during the window that it was discovered in. Right? And so all these things factor into data retention, and it's always going to be a balancing act, right? So, I kind of highlighted there want versus need versus cost. In theory, it'd be great to just say, let's just keep data forever, right? I don't know if I'm going to need to fix it. I don't know what sort of future analysis I'm going to need. I don't know what compliance regulations are going to change that need me to keep N years worth of data. So let's just keep it forever, right? But that might be what you want, but that could be really expensive, right? Especially if we think about like a traditional ETL model of all this data needing to be retained at the source, right? That could use on-prem storage, high cost storage. So you kind of are always balancing how much data do I want to keep? How much data do I have to keep? And then what does it cost to kind of figure out someplace in between want versus need, right? And it's both cost from a financial, dollars and cents perspective, but also performance, right? Keeping 15 years worth of transactional data in a source system is going to slow down processes that need to scan, those potentially very large tables of information. So ETL, right? Traditional ETL has been used for years, right? I'd say dozens of years, probably longer than that. And so all of a sudden, we kind of came up with, what if we could, right? What if we could kind of change the model that we integrate our data? And thinking through this transformation layer, we already have storage and compute resources in our data warehouse, right? Data warehouses can store data and they can compute data, right? We already have it. So do we need this extra layer to handle nothing but transformations, right? And another what if, right? What if this data warehouse could have access to all of our data? Right? So full visibility into how the data was transformed and modeled in the way that produces our final analytics. Right? This is especially useful in like data science type workflows where, the people consuming this data might want to see the full lineage of how a particular piece of analysis came to be, right? What did our raw data look like? How was it cleansed? How was it filtered? How was it transformed? How was it aggregated? And how did it end up in its final analytics ready state? Right? And what if we could retain data in the warehouse, right? We didn't have to rely on our source systems retaining data indefinitely. We could retain data in the warehouse for as long as we wanted it while balancing cost, right? And this is where ELT started to take shape, right? As a way to address some of these considerations and challenges that we faced with ETL. ELT really couldn't have happened. I mean, it theoretically could have, but it probably wouldn't have become as common as it is had it not been for the modern data warehouse, specifically the cloud data warehouse, right? Platforms like Snowflake and Redshift, which I recall from the polling, very heavily used by lots of you that are on the call today. So fueled by kind of this modern data warehouse that is cloud native, ELT simply switches the L and the T, right? It's in its most basic definition. So we're going to extract data from our source systems. And by the way, in between when ETL was kind of born and ELT became a thing, our source systems changed quite a bit too. Right? We've got raw data stored in various file formats on storage like S3 or Azure Blob. We've got streaming inputs now to handle real-time event generation. But then we also have our operational application databases that remain important. So these sources have changed, but now we're not going to worry about transforming data second. We're going to extract it, load it into our data warehouse, and then transform it in all the various ways that we need to transform it. Right. So if you look over on the right with our targets, kind of the result of this process, extract and load, and then I just put some table references in there. Let's load our raw data into the warehouse, right? That staging table perspective or the staging zone, whatever you want to call it. That's going to be now our raw extracted data from our source. We'll then transform it into a different set of tables or a different warehouse or different, section of our warehouse infrastructure. And we'll do all the things that we used to do in a separate layer, enriching, cleansing, filtering. We'll do that in the data warehouse into a separate set of objects, right? And then if we need to aggregate that data into analysis to provide our, financial reporting, we'll then do that, but on top of data that's already in the data warehouse, right? So really, fundamentally, all ELT really did was change where the transformation happens in terms of your data integration architecture. Instead of happening in between loading it into your warehouse, it happens after data has been loaded into your warehouse. Right? And so I mentioned this really took shape because of the introduction of these modern data warehouses, or these cloud native data warehouses. And a lot of that came from the fact that storage became really inexpensive, right? So these data warehouse platforms that leverage cloud native storage could now store terabytes to petabytes of information and do so very cost effectively, right? We can now kind of shift from that want versus need more to the want side of the equation, right? Let's keep data forever in case I ever need to use it. And because storage is cheap, we can do that at a very low cost, right? So whether or not it's actual unlimited data retention or just, the number of years that you decide you need, it became much less expensive to store data long-term in some of these, cloud native warehouses. And because of this, you then get the ability to replay data transformations on data in the warehouse without having to go back to our source systems. You also get full visibility into the lineage of your data transformations from the warehouse itself, right? So those data scientists that really want to not just see these refined data sets, but inspect how data move from stage to stage, you have it all, right? You've got your staging data, your cleansed data, and your aggregated data all accessible in one place. This also enabled you to much more easily use the same raw data for multiple purposes, right? That use case earlier where, you started ingesting this data maybe for financial reporting, and then you decided to use that same data for predictive analytics, right? Once you've got all the data in the warehouse, it makes it a lot easier to then go and carve out different purposes of that same source data, right? But naturally, ELT solved some problems, but kind of introduced a few others, not the least of which was once data gets into these warehouses, it's really hard to get it out. I was actually listening, I wasn't planning on mentioning this, but I was listening to the keynote at the Starburst conference this morning, and he quoted, the CEO of Starburst quoted that data lock-in is the worst type of lock-in, right? And that was going to the fact that once you get data into these data warehouses, it's really, really hard to get it out. And the challenge of that, or part of the challenge of that, or I should say reasons of that, is that most of these warehouses store data in a proprietary system. They're not using open file formats. They're not using data formats that can be easily exported or converted out of that warehouse logic. So that's a big risk and something that a lot of customers have to consider when they consider these ELT processes, right? Once data gets into the warehouse, we're relying on the warehouse for data retention and all of our transformation processes. What happens if we ever need to transition away from that? And is our data now locked and jailed inside of that warehouse architecture? Another challenge with data warehouses in general is that while storage is really inexpensive, compute is not, right? And these modern data warehouses, they separated storage cost from compute cost, but compute cost can still be very high, especially when transforming large volumes of data, right? So if we're just loading data into a data warehouse and keeping it forever, that might not cost us very much until we actually need to use that data for something, right? And now if we need to provide a transformation on years worth of data at terabyte scale, we're going to be spending considerable amount of compute resources to process all of that data as a batch. And in doing so, we've kind of defeated the inexpensiveness of our storage with expensiveness of compute resources needing to transform that data. And another thing to consider is that ELT was really founded off of batch processing, right? Let's take data as a batch and load it into our warehouse and do that on some frequency, right? Daily, hourly. It wasn't really designed for real-time processing. There's a lot of reasons for that. First of all, loading real-time data into a warehouse, again, can be very expensive, right? One way to mitigate compute cost in a data warehouse is to let the warehouse, quote unquote, sleep, right? So that it doesn't have to process data continuously 24/7. But with real-time data, especially as companies start investing in streaming technologies, do I want to load real-time data into a warehouse and then require that warehouse to stay running 24/7 so that it can process that data? So data freshness becomes a challenge in sort of a real-time model. The other challenge with streaming sources in an ELT world is all these kind of what if scenarios that are fairly common in streaming architectures, right? What if the stream goes down for an hour, right? What do we do? Do we just lose an hour's worth of data? Is there a way to catch up when the stream gets back? What if the stream contains duplicate or late arriving events? This is a very common problem with streaming technologies, in that writing to a stream, in most cases, when you write data onto a stream, you can guarantee at least that an event or a piece of data shows up on the stream at least once or at most once, but it's very hard to guarantee that it shows up exactly once. So because of that, you often end up with either duplicate events that you need to process or missing or late arriving events that you need to process, right? Where data shows up on a stream minutes, hours, maybe even days after it was initially generated. And then also these streaming technologies were in many ways built to allow for and encourage schema evolution, right? Streaming technologies, you're just loading events onto let's say a real-time Kinesis stream. And there are ways to lock down that schema. I know data contracts is a big concept being discussed now. So there are ways to mitigate this challenge, but fundamentally, when you load events onto a stream, that stream could take any schema format that you want it to. You could add columns, change data types. And data warehouses in general weren't really built to support rapidly evolving and dynamically changing schemas. So all these things now need to be considered when, especially as your business maybe starts to adopt or consider more real-time use cases or streaming type use cases. Right? So where does that kind of put us, right? We've kind of now built up here an ELT world or ELT technology as described, where you leverage the data warehouse for transformation, right? Extract it from the source, transform it in the warehouse. And there are several benefits to that, right? One I haven't even discussed yet, but is really important, is that I alluded to the fact that some of these legacy ETL systems use proprietary programming languages to build out transformations. Well, one of the benefits of ELT, once you get data into the warehouse, you use the warehouse of the language to then transform that data, right? Which is most often SQL, which is the most commonly known and understood language by data professionals. A lot of data professionals really like the fact that they can write transformations in SQL because they're transforming data in the data warehouse, right? But ELT has its benefits, has its drawbacks, which we've discussed. ETL has its benefits, right? And its drawbacks, which we've discussed. So your choice in terms of building out a data integration architecture is really one out of kind of comparing and contrasting the benefits versus the drawbacks based on the specific use case that you need to deliver in terms of your data integration practices. There's no right answer. Obviously, there's no right answer 100% of the time, I should say. But there are certainly strengths and weaknesses of each approach. Now, over the past few years, kind of an adaptation of ETL has started to become common, or at least something that customers are considering. And that's kind of going back. I don't want to say going back because it's really going forward, but it's kind of embracing an ETL model, right? Where transformation is still happening before data gets to the data warehouse, but using a data lake to process those transformations. Right, so the architecture almost goes back to what I showed at the beginning of the presentation. You have this separate infrastructure to provide, to run transformations on. The advantage or the difference is that we can now use a data lake to process these transformations, which allows us to use much more cost-effective and commodity resources for storage and compute, right? Instead of having to set up proprietary closed systems that do nothing but transformation, we can store, for example, raw data on S3, keep it for as long as we want to keep it, and we can use commodity compute resources, containers, cloud-hosted instances, right? We don't need purpose-built solutions to transform data because we can use our data lake resources for that. So this sort of architecture now kind of gives you the best of both worlds, right? You get the benefits of traditional ETL, reducing compute requirements in the warehouse in terms of being more cost effective. You avoid data lock-in. Remember, most data lakes store files in open file formats, right? So it makes it a lot easier, to push data to different locations. We're not locked into a single proprietary version of data forever. But you also get a lot of the benefits of ELT, right? We separate the data retention requirements from the source system. We don't need to keep 7 years worth of data on our source. We don't need to keep 7 years worth of data in our warehouse. We can keep it very cost effectively in a data lake, right? So, and data lakes also serve as really useful staging locations for streaming sources. Right? A lot of streaming technologies are now starting to feed into data lake architectures because, again, it serves as this intermediate layer between the streaming source and the data warehouse, where we can kind of solve some of those problems with streaming technologies we talked about a few slides ago, right? Historically, the challenge with data lakes is that they're very similar in concept, but they can be very difficult to manage, right? I've seen entire presentations built around avoiding data swamps, right? I saw this years ago. Data lakes started to really become top of mind for a lot of IT or data practitioners. And the idea with the data lake is, let's just start throwing all of our data into S3, right? We'll worry about it later. But what ended up happening is that data lake just became a swamp of information that nobody could get any meaningful use out of. So this is where kind of Upsolver steps in and really tries to help customers approach this ETL and ELT scenario with a single platform, right? And so kind of using a data lake as a transformation layer for use cases where you need to write data to a data warehouse, Upsolver allows you to do ETL using the flexibility and economics of the data lake to transform your data. Right, so reading data from a source, transforming it in a data lake, and then writing those refined data sets out to your data warehouse. For use cases where you don't need a data warehouse, and these likely exist, Upsolver is ELT, right? We can build data transformations and build our data products in the data lake that directly serve analytical use cases. Right. This is a change in architectures that some companies have already really gotten a lot of value out of. It's maybe for a lot of our use cases, we don't need a data warehouse. right? We can leave data in S3, manage that data through a variety of processes, and then serve using any number of lake-based query engines directly our analytics, either reports or machine learning models, whatever it might end up being. The way that we've done this with Upsolver, and then I'll give you a quick demo, is that Upsolver takes your source data, right? So we read off of the most common sources used in modern data architectures, streaming sources, file sources, database sources, and we ingest that data into our stateful streaming engine. So Upsolver SQL Lake processes everything as a stream. Even your traditional batch data, batches can be processed as streams. We just process each row in a batch as an event on a stream, right? So we bring that data into Upsolver and we start to process it using our stateful streaming engine, right? We can build a variety of data lake tables on top of that data to service different needs, right? Your staging data, your cleansed data, your enriched data, your aggregated data, all of that can be managed inside of your data lake. And then you can either write that refined data out to your data warehouse in more of a ETL model using the data lake to transform data, or you can leave that data in the lake as a data lake table and query it using any number of established query engines, Starburst, Dremio, Athena, Presto, Trino. There's lots of them out there. Anything that can read from an Upsolver managed catalog can go ahead and return data from the data lake itself. So architecturally, that's really how the Upsolver ETL approach or ELT approach can function between your source data and your desired target. Now, going back to, isn't the data lake hard to manage concept? Yes, it is. And that's one of the things that Upsolver is going to try to make much easier for our customers. First of all, just the process of ingesting or extracting data, transforming data, and writing data in this streaming real-time fashion is all done using SQL. You can see some example code over on the left. This actually, we mentioned one of the benefits of ELT is that your transformations can be written using the language of the warehouse. In other words, SQL. Well, that's the same way that we interface with Upsolver SQL Lake, right? Everything is done using SQL, from the creation of connections to the staging of data to the transforming of data. So you're not forced to write, Python or Spark or any other, programming interface to actually transform data. But then also, if you look over on the right-hand side of the screen, SQL Lake's going to do all of the manual orchestration typically required in maintaining an efficient data lake. We do it all for you, right? So when you write your data pipelines or your data ETL processes in Upsolver SQL Lake, we automatically infer the orchestration needed to optimize the data lake throughout that process. We can scale up and down as data volumes change. We can shard out data for increased scaling of data that's needing to be read or written. We manage the partitioning of data. We handle schema evolution. We optimize your data lake for querying. All these things happen automatically to make your data lake and your data pipelines much easier, especially at scale. Right. So just to kind of see how this works, in Upsolver, this is the Upsolver user interface. Let me zoom in here just to give you a slightly larger view of what we're going to be looking at. You'll see down the left-hand side of the screen, you've got worksheets, jobs, and clusters. These are the components of Upsolver, the SQL Lake interface that you're going to build your pipelines with. Worksheets is your development environment for writing SQL. Jobs are the processes that move data from point to point, and clusters are the resources that process data. Now, if you are interested in trying out SQL Lake for yourself, we do include dozens of out-of-the-box templates that show you how to work with various inputs and outputs, as well as perform various types of transformations. So it becomes really easy to get started with SQL Lake. If you've got data in Kafka that you want to write out to Snowflake, you can likely find a template that matches that source and target combination and use that to start your investigation of the solution. That said, I've got a worksheet here called Data Producer. And think of this as like a data engineering workflow where you've got to read data from source systems and start the process of transforming and refining that data so that our data consumers can start to create analytics on top of it. So we can create connections that maybe read from S3 or read from Kinesis or Kafka using a very simple and familiar SQL syntax. We can create data ingestion jobs that read from sources and load into staging tables. Here's an example of a job that reads from S3 and loads into a staging table in our data lake and does so continuously, looks for JSON data, and loads data from our sample into this bronze table that we've defined as our raw data. And then maybe this data engineering workflow is one where we've got our raw data, but the first step is we need to cleanse it. Cleansing could be, if you look at the transformation job here, applying an MD5 hash to an email address, right? We don't want PII ending up in our analytics, so let's hash it so that it's protects some of our sensitive information. Maybe we need to normalize some data. It shows up in mixed case in our source. We need to normalize that for aggregation downstream. Maybe we need to calculate some data corrections. Maybe our countries show up as both USA and US, so we need to normalize that in our output. So we can create, in this case, maybe a data cleansing job that builds a silver table that has refined data that we can now better use for transformations. We could also possibly create redacted tables, right? We've got terabytes of incoming data. We don't need all of that particular analytics use case. So we can filter data just by a simple where clause, right? Now we've maybe got a redacted use case where we write a subset of columns and a subset of records into a silver table for analysis. Or maybe we also want to flatten data. Right, this is fairly common, especially with semi-structured file formats like JSON, where we have nested and hierarchical data elements or array structures that we need to deal with. And in order to properly analyze this data, we need to flatten that data so that we can aggregate it downstream. Right, flattening data in an Upsolver SQLite workflow is really as simple as just kind of applying an unnest function to some SQL and then writing out a flattened result set to a particular, in this case, silver table that we're going to work off of. Right. So once we build these jobs, right, our ingestion job and our transformation jobs, those jobs now run continuously, right? So you don't have to schedule these jobs to run once an hour. Your data freshness is really as frequent as up to a minute or near real-time processing, and jobs run continuously ingesting and processing data through the pipeline. Now, possibly for an analytics use case, we might now need to pass this data off to a data consumer, all right? This data consumer now is going to take these data sets that were produced by our data engineers and work them into analytics-ready objects, all right? We can inspect the raw data in SQLite. These are those data lake tables we referred to earlier. If we just want to kind of see and inspect the data, this is using an Athena connection, but we could use any data lake based query engine to expect our raw data. And then we can also build data transformation jobs using this single infrastructure for producing our data products. And if we wanted to do more of an ETL approach, where we're transforming data and writing to Snowflake. Here you can see an example of a job. It writes to Snowflake once per hour and applies this SQL-based transformation to our source data. Right, this is doing an aggregate use case. We've already flattened our data from our source system. We're now aggregating it by item ID and writing the results into Snowflake and keeping that data up to date with 1 hour freshness, right? And with this job running, I can transition into Snowflake and we can see our transformed data set, starting with source data showing up in S3 or on a stream, transforming it in the data lake, and then writing this refined data out, in this case, to a Snowflake object, right? Our business users are going to have that transformed data set in the format that they need, kept up to date with, near real-time frequency or whatever the business requires. Or similarly, we can do the same exact type of transformation in more of an ELT model. It's just where the end result of this transformation is a data lake table, right? So the same transformation, but instead of writing into Snowflake, writes into a data lake table. Data lake tables managed in S3 using the AWS Glue data catalog. And now anything that can query data from a Glue data catalog, be it Athena, Starburst, Dremio, whatever your query engine of choice may be, can now read data from this refined data set that SQLite is producing for you. Right. So that's effectively the upsolver approach to data transformation, right? Again, either ETL or ELT, all in a single platform based on where you need to send your data to, and using the data lake economics to transform and process streaming data in motion at scale in a very cost-effective way. That kind of ends my portion. Hope that was interesting. Definitely want to accept any and all questions. I'll keep an eye on that as I pass it off to Bjorn, and then we'll address questions at the end.
Jason, thank you for walking us through that comparison of ETL and ELT. I think it all gives us some things to think about and what might work best in our specific use cases. And just for the audience, I'm just going to close out with three very simple slides. What are some of the questions that we hear most frequently? And those, what do we think about? Just a very quick summary of some of the unique aspects of SQLite that Jason shared, and then some ways to engage if you're interested. So when you think of these questions, I've kind of looked at them from a little bit different angle. The first question is really thinking about what is the demand and supply for analytics ready data. I think what's happened is we've all seen an increase in the amount of analytics ready data that's being requested by our data consumers, whether they're internal, employees or whether they're external customers. And what we're not seeing is the ability for us to hire data engineers at the same pace as the demand. So a lot of the questions we get around whether ETL or ELT or some combination of the two, what helps us take some of the load off the data engineers so that they can go ahead and focus on the most important aspects of that to hit the backlog and meet the increased demand that's happening in our environments. And that actually kind of loads into the question too. I had the opportunity to attend Data Day Texas a couple of weekends ago, and the opening keynote was around data mesh. And so a lot of the comments that were coming from the attendees as they're walking out of that session were, is there a benefit to giving data consumers direct access to the raw data? Yes, some of them know the data and the business better than maybe some of us do, but are there challenges and advantages to that as well? So how do we balance both of those as it relates to figuring out what strategy we want to take? The other one that's been happening, I'll say really even more recently, I know it's been for years, but at the end of the day, it's been the last month, I've really seen it tick up. Jason and I were having a conversation with a client last fall, and the leadership team's like, well, if we have data once or twice a day, we're good. They started polling their data consumers, and the next thing you know, a couple of months later, they come back and say, well, can we get that down to an hour? And then the bigger question I think we all have to ask ourselves is, at what level of data freshness do we continue to add value for our organizations and our data consumers? Like Jason mentioned, is it 1 minute? Is it 15 minutes? Is it an hour? Is it a day? And then the last thing could actually be reframed as, what are vendors doing to actually make, I'll call it the cost and predictability of the ROI for data projects easier to calculate. So that's really the question we're getting is, you've got all these different moving components inside that structure from, your beginning source systems to your data warehouses and tables. What are vendors doing to help make that easier for us to calculate data projects and their ROI? And so there's a couple of things that Jason brought out in the demo, and just want to write those out. And the North Star when developing SQLite was really, how can we help customers use SQL like they do in their data warehouses and be able to write a continuous data pipeline in a very simple format, and then be able to do some of the things that take the load off of data engineers and things that data consumers won't be able to do, such as inferring orchestration, scaling, performance optimizations, and things like that. And then the other thought process was, what can we do to integrate a streaming engine, a very efficient state store and data lake economics to be able to blend seamlessly both real-time and the batch data and historical data, and then be able to support things like high cardinality joins, aggregations, and even upserts. So those are some of the unique aspects that SQLite brings to the table. And the last one was to answer the last question on the previous slide, which is, what are vendors doing to make these things more predictable in terms of cost and ROI? And Jason alluded to a little bit in the beginning, but we moved to $99 a terabyte of data ingested. The number of users, the number of transformations, the number of pipelines are all included in that. And then for our customers who have significant amounts of data, a lot of pipelines, want a higher level of support, there is the option for a annual platform fee, which provides unlimited clusters, support, access to folks like Jason. And then the good news there is that's a fixed cost for the year. You know what your variable costs are, and it makes that data project much more predictable. And going back to that question, want, need versus cost. So in terms of, what are ways to potentially engage with us? I'm a hands-on person. So while it says account executive in my title, I started off in IT and was a solution architect for a while. I like to just dig in and try some stuff out. So we offer a 30-day unlimited trial. There's no credit card, just put in your information. We don't even care if it's your personal email address. We just want to give you a chance to get your hands on it. If you're someone like some of my friends who are like, hey, I've only got an hour, I want to fast track that thing. Jason runs a SQL Lake hands-on workshop. The next one is March 7th. I think Jason put that link in the chat for you. And that is where you get an hour. You actually get hands-on with SQL Lake. You'll deliver, 2 or 3 streaming pipelines that you've created, and you walk away with that unlimited trial to work with. If your questions are deeper level or you're not getting everything answered that you wanted to on this particular session, you can also contact us directly. I run the western half of US and Canada, and I can be reached at bjorn@upsolver.com. Dave runs the east. And if you are in one of the other locations, whether it's Europe or Asia, we have a peer over in that direction, and we can make sure we get you to the right resources, whether it's a person on commercials or person on technical, or maybe even at the product level. So, with all that, we've got a few minutes left for questions, but we want to thank you again for attending and look forward to your success with continuous data pipelines. And wherever you are on that journey, and wherever you decide, whether it's ELT in the warehouse or ETL or a modern ETL. And with that, we can see if there's any other questions sitting out here in the Q&A session.
Cool. Yeah, I've actually got a few that I'll go ahead and answer. So one question was about SQL Lake, the Upsolver platform, and specifically, is it open source? So it is not open source software, but it does use open file formats. So we talked about vendor lock-in and data lock-in specifically being a challenge that organizations might want to prevent. All data in your data lake is effectively open file formats, Parquet typically, but there's a few options there. And we can also write data out to a variety of file formats. So there are some customers that are using SQL Lake and using it to write data out, maybe not even to Snowflake or Redshift, but writing it to JSON files sitting in some unmanaged S3 bucket that they have full access to. So generally speaking, the fact that we use open file formats and the fact that we use more or less a programming interface that is accessible and recognizable to most practitioners can kind of avoid that lock-in that we talked about earlier. There was another question. Sorry, let me read this one. Oh, gotcha. Yeah, is SQL Lake a platform or a format? Oh, good question. Yeah, so SQL Lake is a platform, right? So SQL Lake is the Upsolver platform for streaming ETL using data lake to perform transformations. So when we're referring to SQL Lake, we're talking about our infrastructure that, again, ingests data from sources, transforms data in the data lake, writes data to targets. That effectively is SQL Lake. And like I just mentioned, the file formats that are used are effectively open file formats. So there's no lock-in in terms of the data formats that we're leveraging. There was actually another question that came up that's similar around where SQL Lake runs and where it's installed. And that's a great question, because SQL Lake actually runs inside of your AWS VPC. So this is software that you maintain full governance on. In other words, again, let's say kind of extending upon the open file formats, they are files that are stored in your AWS account, right? You maintain the buckets, you maintain the firewalls, you maintain the encryption, you maintain the security of that entire infrastructure, right? So SQLake leverages resources inside of your AWS VPC. And again, that gives you full control and governance over the entire end-to-end processing of your pipeline. And the open file formats give you full ability to leverage those files in any way that you see fit. There was a question that came up about cost. I know Bjorn referenced the cost in one of his slides. There's two sides to SQLake cost. All you're going to pay Upsolver directly is data ingestion cost, $99 a terabyte. That was really done, again, to make the data pipelining process very predictable. And so if you have a project on the horizon, you expect 5 terabytes of data per year to be generated by that project, you're going to know upfront what the Upsolver cost is for building pipelines on that data. We don't charge for transformations. We don't charge for number of outputs. We don't charge compute units. Now, there is a secondary part of the cost, and that's the AWS infrastructure cost itself, that it will be paid directly to AWS. But we're doing lots of things in SQLake to minimize that cost. We use EC2 spot instances to get you the best pricing on compute when compared to on-demand or reserve instances. We're using, again, S3 storage to process all of our internal storage, and you've got a lot of flexibility in the type and cost of that storage that you leverage. We also allow you to easily manage data retention, which is a way you can keep costs down, really match retention requirements to your business needs. We also scale resources up and down based on scaling properties that you set in SQLake. So you can scale for latency or scale for cost, depending on what your strongest requirement is. And as a streaming engine, it really allows us to smooth out your compute cost as you process data, right? A lot of customers have told us when they went from daily batches to more of a streaming pipeline approach, their cost was driven down, even though the frequency of data transformation was higher. The compute needed to transform data event by event was much lower than the compute needed to transform massive volumes of data as a large batch, right? It allows you to use smaller EC2 instances, use them more frequently, but at a lower scale. So compute is something that a lot of customers come to us as a challenge. They're trying to build out a data pipelining architecture. They obviously want to keep cost as low as possible. And again, we handle that both on the licensing and predictability side with Upsolver, but also in helping you maintain a very cost-effective AWS infrastructure to process that pipeline.
Yeah, and we did have one question here at the end here. It says, can I have access to the slides in session? And absolutely, we did record this session, and we will be sending out the link to that as well as the set of slides.
Excellent. Yeah, and when you all leave the meeting, some have already dropped off. I know we're 2 minutes past the top of the hour, so we appreciate all of you sticking with us. There is going to be a survey that launches. No pressure to fill that out. Just if you'd like to give us any more information, we'd love to hear it, both feedback on today's session as well as whether you'd like to learn more about Upsolver. If any of you want to make sure that you get the recording and slides as quickly as possible, just say that you'd like us to reach out, put your email address in, and we'll send you all the resources that we have. We'd also love to have any further follow-up conversations if there's any further discussion you'd like to have around building your transformations, whether that involves Upsolver or not. We're open to any and all conversations. So thank you, everyone, for joining today. I know we're a few minutes past the hour, so we'll get you back to the rest of your day. Bjorn, anything you want to wrap up with?
No, I did see we have one person like to contact directly. We'll go ahead and reach out to you. But otherwise, again, thank you. Have a great rest of your day, rest of your week and weekend. And this will conclude our webinar.
Thanks, everyone.
You want to stop the recording?
Find the button.
It's up on the upper left.